today I want to talk about some of the test and measurement challenges we're seeing in these new pluggable coherent optics. So coherent optics have played a major role in data transport for quite some time, but they tend to have been used in closed systems and engineered links. But recently we've seen the emergence of pluggable digital coherent optics, which led to a more open multi-vendor ecosystem. This started with 100 gig CFP, and now we see significant pull, as Jeff's slides illustrated, for 400 gig class coherent modules in more compact form factors. Of course, the broad range of applications from DCI through to classic DWDM and transport. And we're aiming for an open multi-vendor ecosystem, and of course that does press more demands on the test and measurement ecosystem, but also means a very successful ecosystem if you can keep this open multi-vendor backed by robust standards. So the presentation today will outline some of those challenges from the photonic layer through to module management, which again, Jeff has mentioned recently. This is another take on the form factor zoo out there. Now, it doesn't mean lots of form factors are wrong. Some are actually very, very good at what they do. But as Jeff mentioned, we are tending to consolidate on one or two, including the QSFP type family, the SFP family, and the OSFP family as well. And these today are the most popular, but we still see applications today, including the CFP2, getting a new lease of life with the new 400 gig class DWDM modules. The vast majority of photonic interfaces traditionally have been direct detect, but again, as my colleague showed, we are seeing more and more applications for coherent interfaces as well. On the electrical side, we are transitioning from NRZ-based to PAM4 electrical signaling. I always say this, but I do feel optical pluggable modules are an absolute marvel of engineering. They bring together really state-of-the-art photonics, mechanical engineering, thermal engineering, and of course, high-speed electronics, signal integrity, and also now firmware with the emergence of DSP playing a very big part in optical modules as well. And of course, all of these have to be produced in very large numbers to play in a multi-vendor ecosystem. Here's a simple cartoon of one such example, a 400 gig QSFP-DD, and just highlight some of the challenges from signal integrity, going in on the host side, the module management, which Jeff has alluded to, orchestrating the high-speed electronics, the photonic side, and of course the photonic side as well. And these are all made to very, very aggressive price expectations. So lots of engineering work going on there. And of course, for test and measurement, lots to do to make sure these can all work in an open ecosystem. So today, with the 400 gig modules, we have seen a whole new range of challenges for test and measurement perspective. I think two of them I'd like to highlight. One has been the move to PAM4 modulation rather than NRZ. With PAM4, the voltage levels are close together, and that does mean more impact of noise. And of course, now most of these links do have a FEC as part of the standard. So now the simple testing for errors, no errors, moves away to more one of understanding what's the nature of the errors and what's the threshold for my FEC. Another significant challenge, as Jeff alluded to, has been the adoption of more complex but more comprehensive module management with our CMS4 and hopefully to transition to CMS5 in the future. This is a far more complex stateful module management, but also allows the more module orchestration to do much more. And we've also seen a speeding up of the module management buses. The I2C interface traditionally ran at a few tens of kilohertz, but now we're seeing buses run at megahertz as well. And of course, any real system may have to play with both legacy modules, perhaps ones of 40 gig generation, together with 400 gig modules, all running with different expectations of module management and interface. And of course, we haven't even yet touched the photonic interop, especially with the higher order modulation. So I'd like now to take a short introduction to pluggable digital coherent optics. I think this illustrates very nicely the evolution. Traditionally, coherent optics have existed on line cords focused on DWDM transport based on large line cards with marvelous custom ASICs and photonics, but very much engineered links in a single vendor integrated ecosystem. But if we want to move to more broad open application space in an open ecosystem, well, pluggables are one way to go. So now we see the emergence of pluggable coherent optics working in a multi-vendor ecosystem backed up by robust standards and MSAs. This is really going to drive broad application take-up. Before we dive deeper, I do want to make this, there is a note, there are two types really of pluggable coherent optics available. analog coherent optics and DCO. The focus today is mostly on DCO, but analog coherent optics, if you like, are a small subset. In this case, the module really contains the photonic front end and hands off high broadband analog signals, where the host itself will do the digital signal processing, decoding of the analog signals into the bits. The digital coherent optics, which is really the bigger, exciting area now for pluggable coherent, you integrate not just this very complex coherent transmitter and receiver, but now you also have to integrate the DSP, the framing, and everything else. But you hand off in a standard digital interface. You do meet complex module management, but of course, it means you have a standard client interface. And hopefully, if your host can handle the power and cooling, you can then mix traditional client and coherent optics, and part of that pay-as-you-grow module. So today there are three exciting form factors: Coherent CFP2, QSFP-DD, and OSFP. All these include a complete coherent system. They're designed to plug and play into standard client optics, albeit with extended power management and advanced MIS. Vendors have been shipping 100 gig and 200 gig modules for quite some time now, but now we're seeing a lot of excitement around the CFP2 for 400 gig, QSFP-DD for 400 gig applications. These have been sampling now. We actually have seen several interrops as well. So this is a real ecosystem happening now. I think if ECOG had been real, we would have seen some other real interrops as well. Unfortunately, I think we'll have to wait and through to OFC to the for real open interop. Multi-services, Ethernet and OTN can be supported as well for the CFP2, while the QSFP-DD tend to focus more on Ethernet applications. They are two distinct segments. We see it as the 400 gig CFP2 focusing on the multi-service classic DWAM applications where you're carrying Ethernet, but also other things, FlexO, FlexE, even fiber channel. The QSFP-DD 400Z applications much more focused on the Ethernet out to 100 kilometers reach, and really backed by the emerging 802.3 CW standards. I think one of the big ways of looking at the impact of coherent, especially for test and measurement, is traditionally photonics really only touched the ROSA and TOSA when it came to testing. And the photonic domain was photonic, okay? But now with the emergence of coherence, that photonic testing reaches deep inside, not just the photonics, but the electronics and the DSP as well. You can see there an image of an integrated coherent receiver. So the photonic domain really now is optical, electrical, but also firmware. All of that is impacted by what goes on in the photonic domain. And I think this cartoon sort of illustrates it a bit better. On the left side, we have the photonic domain, and we've moved away from just simple intensity and wavelengths to much more complex parameters: OSNR, area vector magnitude, power spectrum. And through on the right-hand side, we see the protocols, the bits, the error rates, and the other things as well. But of course, all of that is orchestrated by the module management. So we can see, as well as having a photonic component inside the module, a large DSP content, and you can see below we break out just some of the challenges and some of the functions that DSP has to do, because that DSP is silicon and firmware. And then there's the high-speed electrical interface, which goes between the module and the host. And finally, of course, the management interface, which orchestrates all of this as part of a complete integrated host module. So as we mentioned before, that DCO module is a fully integrated DWAM system, including the complex photonics, the DSP, framers, host interfaces, and management. All of that must be controlled. That's done over a serial management interface, backed up by standards, including extensions to things like CMOS. Multiple parameters, multiple housekeeping things must be done. And as you can see, with the emergence of CMOS for client optics, we see even more demanding requirements for coherent modules as well. And all that must be orchestrated and done together with what's going on with the high-speed host and photonic domain. So that's an area where we do see several test and measurement challenges to make sure that we can really have an open, easy to play ecosystem. I want to give you now a couple of very simple examples of things that we have to think differently about. Okay, but the first thing, before you dive into DCO testing, you want to have the right sort of environment, one that includes power, cooling, the right sort of native electrical I/O, controls the PHY layer, because there's still a lot of PHY layer unframed testing, but then we move on to the Ethernet OTN, the management interface, and all the other things as well. And of course, as I say, I would recommend the VIAVI product line for this. If we look at just some of the functions DSP must do, it's got to look at things like loss of signal. And as Jeff mentioned, even with client optics now, the management of loss of signal is very demanding. The DSP itself must do the CDR, checking, locking in range. The chromatic and polarization dispersion is also done in DSP. Then things like error vector magnitude, OSNR are calculated. And eventually you get to your FEC, and then the FEC will do some correction, hand that off through the framer and protocol off to the host via the high-speed interface. So that silicon chip is doing a tremendous amount of work, orchestrated by, of course, lots of very complex firmware and DSP algorithms. So let's look at a very, very simple test. As Jeff mentioned, a past service disruption was a very simple test of optical modules. You interrupted the optical signal, you brought it back, and you looked at how the module recovered. And I think Jeff mentioned the figure of 15 milliseconds. In a coherent, this is much more challenging because you may have multiple carriers present in that DWDM system. They could be 80 or more carriers at the front end. In some cases, the optical module must determine its carriers gone and not falsely track any other carriers as well. So in this case, we can generate a multiple carrier thing, interrupt the particular carrier interested, and make sure the module correctly identifies that and then takes the right behavior. And that's a combination of the DSP, the microcontroller, the firmware, communicates that correctly over the management interface. And of course, then when that signal is reasserted, that process works correctly and there's no ambiguity. And of course, especially at host management level, you understand what's gone on, that module's recovered correctly. Lots of signaling to go on there between the host and the module, and a tremendous amount of software firmware needs to work correctly before that can happen smoothly. Other parameters include chromatic polarization dispersion. Especially the polarization, state of polarization can change very, very rapidly in real systems. Having DSP that can track that state of polarization correctly, compensate for it, and of course relay it to the host management system is also very important. So now our optical test system, as well as including optical signal level, etc., we have to also include testing for testing chromatic and polarization mode dispersion, and making sure the DSP, the firmware, and the algorithms can track that, and also that can be correctly reported over that module management interface. OSNR. In the good old days of simple client optics, an attenuator really was all that was needed. You'd look at the signal level, look at the bit rate, and look what happened. But now with coherent modules, really OSNR is a much more meaningful parameter. So the ability to tune out the OSNR and then look at how things like the error rate changes with that, look at the performance of the DCO's module FEC, embedded deep inside that DSP is going to be very important. Making sure the right threshold alarms are set. So as a link degrades, the OSNR is tracked, measured, and the module then can relay the state of the OSNR over to the host correctly. So the host then can decide to go back on a fallback link or take other corrective action. So again, this is a test which involves physical layer photonic parameters like OSNR, but also deeply involves the DSP, the firmware in the module, and of course, the module host software. So here's a simple couple of examples of how moving to coherent, it actually really does increase the test complexity. Direct detect really, with no disrespect, is simple E to O, O to E. Now with coherent, we have a complex coherent system with a lot of software in the DSP. Simple optical parameters are often used, wavelength, often it's go, no-go testing. Now with coherent modules, many more parameters to be possibly tuned at multiple wavelengths over temperature, make sure performance works there well. Direct detect modules, we typically do those with unframed or very simple protocols, but now, especially with the emerging very complex DSP, we will have framing and mapping, multi-services, multi-flexo, etc. So important to understand the capabilities there for testing and validating the DSP there as well. We already have a very solid multi-vendor interoperable ecosystem with direct detect. This is something now as an ecosystem we're learning with coherent. We've seen some interops, which is a very, very good start. Of course, the interops don't just prove photonic interoperability, we've also got to prove the host, the module management, all the other interoperability as well. But that's moving along quite well. And many of the organizations, the OIF, IEEE are facilitating that. And hopefully, as we open up from COVID in the near future, we'll have the opportunity to work together as part of this open ecosystem to start more and more interop. And of course, another big change, and again, I think my colleague Jeff mentioned this, we are moving from very simple module management control to far more complexity, and that is even exceeded with coherent modules as well, many more parameters, many more things to read off, and make sure you can, really orchestrate that coherent module with your network element. So in the last minute, DCO modules are far more complex than their direct detect cousins. Frame signals really are needed now. We've seen that the DCO plays a big part in the DSP. So, an unframed really can only penetrate a small amount of test fraction we need to look at. Dynamic performance is very, very important in the photonic domain. Even simple tests like surface disruption now are far more challenging than they were in direct detect, and understanding how to do a proper test for coherent modules is playing a big part. All of this must be orchestrated by the module command interface. And we've seen with emergent CMOS 4, and we're keeping an eye out now for CMOS 5 in the future, plays a big part. And of course, that helps that module be integrated into a system to provide a coherent, orchestrated thing. So hopefully we in VIAVI can play our part there. We're looking forward to working with you as part of an open multi-vendor ecosystem. Thank you very much, Glenn.
Well, thank you, Paul. Again, outstanding information, and I'm sure that folks are going to go back and look at some of that reference material. It's really good stuff. I guess, and again, since we're right up at the time limit, I'll have you go and look through the chat to answer questions. One real quick one, you mentioned early on ACO versus DCO, and I would say that, have we made the transition? I know we have, but I mean, do you think we're ever going to go back? ACO was a stepping stone, I feel like, to DCO. Now that we're here, do you see maybe another generation trying that again, or what have we learned through that? What your opinion of what we've learned?
In my opinion, I think ACO did a lot of promise, and it really segmented the market nicely. So experts in photonic technology could really focus on that and deliver top quality photonic performance. The challenge is, of course, the interface. Being an analog, very broadband, made it quite difficult. People did bring successful ACO products to market, but now by incorporating DSP as well, it's much easier to frame a much more open standard. And of course, also we can reuse all those client slots today. So someone bringing to market routers, switches, another element, they can design one interface plug, which can cover everything from, as Jeff's picture showed, 2 or 3 meters of copper cable out to 80 or 100 kilometers of coherent. And that's a really big value proposition, because that keeps the solid thing about the pluggable optics, not just play as you grow, but also covering now a huge, huge dynamic range in reach. So I'm a big fan of DCO.
You and me both, and I think lots of folks. So I appreciate that. Thank you, Paul. Appreciate your insight there.